Hello, everyone, and welcome to our design project. I'd like to thank you all for being here this morning for our project on responsive aerial firefighting aircraft. We are Group 2, the Fireflies, and our team members are Michaela Bond, Shamir Orsico, Dylan Carter, Salvatore Como, Julian Davis, Patrick Hess, Hiroyuki Matsumura, and Annabeth Smith. Next slide, please. Next slide, please. So I guess the first question, what goes into designing a firefighting aircraft? Currently, the majority of aircraft that are tasked for this role are conversions that have been applied to existing aircrafts to turn them into water bombers for firefighters. Over to the right, we show a couple of those aircraft that have been converted. Some examples are the C-130 and the 747. But then when doing this process, it can be inefficient and costly, and you can actually miss out on a few mission statements. So instead, designing an aircraft specifically for the mission lets you fit each detailed mission requirement and meet it. Like, for example, the Martin Mars down in the bottom left corner. Next slide, please.
To design our firefighting aircraft, we followed the objectives as outlined by the AIAA. The aircraft needs to be able to enter into service by 2030. Therefore, we must choose or design an engine that can be in service by 2028 or 2 years before the aircraft enters into service. The aircraft also needed to be able to hold a minimum of 4,000 gallons of fire retardant and be able to drop multiple loads at a minimum of 2,000 gallons each. The fire retardant also needed to be able to be reloaded at 500 gallons per minute, and the fire retardant would have a minimum density of 9 pounds per gallon. The payload drop objective gave the maximum speeds required for this drop speed and drop altitude. It needed to be at 150 knot drop speed at an altitude of 300 feet. The aircraft also needed to operate in a circle with a radius of 200 nautical miles around the airport it took off from, and have a ferry range of 2,000 nautical miles. To meet these objectives, we designed our firefighting aircraft, which the renders can be seen on this slide, and our aircraft was the FF-1853. Next slide, please. So we designed to the 2 mission segments. The first mission segment was designed to complete the payload drops. We have takeoff and then flying at a cruising altitude, operating a circle with a radius of 200 nautical miles from the airport it took off from. So after taking off, it flies 200 nautical miles to the location of fire at cruising altitude. Then it drops the 2,000 gallons of fire retardant at an altitude of 300 feet. Then flies a maximum of 400 miles at cruising altitude to the other end of the operational circle, dropping 2,000 more gallons of fire retardant at an altitude of 300 feet again, and then flying a maximum of 2,000 miles at cruising altitude back to the original airport before landing. Then the next mission flight was the ferry flight. To reach the aircraft had to fly a minimum of 2,000 nautical miles for the ferry flight, but it would not have to carry the fire retardant as it would be collecting it at its final destination. So only fuel had to be taken, the weight of the fuel had to be taken into account for this flight. Next slide.
So for airfoil selection, a variety of different airfoils were considered. However, ultimately the NACA 5 series airfoils were focused on. And in order to compare these and solidify which one we wanted to proceed with, we used a design matrix. And for this design matrix, thickness and efficiency were considered. For thickness, a larger thickness was preferable for a variety of reasons, one of which was that a thinner airfoil is limited in its maneuverability, and this aircraft needs to be designed to maneuver when it drops the fire retardant. A larger thickness also can accommodate larger structural members and enter climb at drop speed. And then it also allowed us to have our wing box bars lighter. So for efficiency, we used XFLR 5 software to plot a variety of different things, one of which is not included on this slide, and it was a coefficient of lift versus angle of attack at a high Reynolds number. And for that graph, the NACA 23018 actually produced the most lift at angles of attack at an angle of attack of 10.5 degrees, which just showed that it performed well for our dash speed. The bottom graph on the slide is the efficiency versus angle of attack at a high Reynolds number. The NACA 23018 is actually the light green line. It's kind of hard to see that, but this graph just shows that it has a smaller drag coefficient at higher Reynolds numbers. And the above graph is the efficiency versus angle of attack at a low Reynolds number. And this was included just to show that the NACA 23018 also performs well and better in comparison to the other airfoils for a certain range of angle of attack at that low Reynolds number as well. So after the design matrix was computed with thickness and efficiency considered, the NACA 23018 was solidified, and that is the airfoil that we proceeded with. Next slide, please. So for wing structure, this consists of the wing box, which has the spars, the ribs, the skin. So for spars, there were two options, there were two discrete bars with I-beam profiles versus just having a closed section. Ultimately, the discrete bars with I-beam profiles was selected because it had more strength given a certain area. And there is a main spar at the aerodynamic center, and as far as dimensions go, you can see that in the figure above. For material, this was selected based off the Ashby chart, which just considers the density to weight ratio. And the leading edges will be made of cladded aluminum, and it's just because it has a glossy finish and it will have less drag. As far as skin goes, things like exterior temperature needs to be considered, and as well as corrosion. And so because aluminum is not corrosive resistant, a polyurethane top coat and primer needs to be utilized, especially in areas of the aircraft where the fire retardant will be in contact with the aluminum. For the frame, a 2017 T4 alloy was selected, and that was because of the stresses of the IB profiles, and that led to that alloy being chosen. Next slide, please.
Okay, so for the fuselage, there was a lot of things that we have considered here, and we went for the structure. We went with the semi-monocoque structure primarily due to weight-saving benefits, and also balances between the loads of the skin and the frame. For the material, we used the exact same material for the wing structure as well, which is 2017 T4 aluminum alloy, primarily because, well, the wing is attached to the fuselage at the top. Now, of course, for the skin, there's the polyurethane top coating and primer, but one thing to consider too is the fire retardant. The fire retardant, when it's sprayed out at the bottom of the aircraft, can actually get onto the aircraft and damage a lot of sensitive equipment. So instead, we would use an epoxy coating for those areas that are exposed to the fire retardant, since it helps to fight a lot of that chemical resistance. It has a lot of chemical resistance, and it's easy to wash off. That's another great thing about using the epoxy coating. Now, in terms of design, the fuselage had a total length of 136 feet, and it had a 21-foot diameter. It has a 21-foot diameter for the fuselage, which you can actually see in the section view here. The radome design was actually designed in such a way to allow the pilots to have a 17-degree over-the-nose view of the aircraft, which is especially helpful for landing. The cockpit resembles that, similar to the A350, and the tail was moved 5 degrees upward. It was actually swept up 5 degrees, so that way it could prevent tail strike, especially during takeoff. Now, that was it. Now, another thing to consider is that for the structure of the fuselage, not all of it was actually going to use the aluminum alloy, because with the Ashby chart, there was a secondary material that was also lighter that we can use to swap out specific areas of aluminum, which is the glass reinforced fiber composites. Those would actually be helpful too in the structure of the fuselage. Next slide.
So fire retardant tanks. So the design requirement of the aircraft is to be capable of dropping 2 tanks, totaling 4,000 gallons of fire retardant. Our tank design will carry 3,000 gallons each and empty them one at a time. The shape of our tanks is cylindrical because it's one of the strongest type of pressurized container. The tanks have a diameter of 7.5 feet. This means that both tanks stacked on top of each other reach a height of 15 feet. The outer diameter of the fuselage is designed to be 17 feet, leaving 6 inches of space along the fuselage skin. For structural support and insulation, leave a diameter of 16 feet inside of the fuselage for the fire retardant tanks to fit, and an overall length of 139 inches, meaning that each tank can carry 3,000 gallons of fire retardant. The tanks are situated above and below each other, and they are placed near the quarter chord of the wing. Therefore, the center of gravity will not shift laterally or longitudinally in the aircraft, only vertically. A vertical shift in the center of gravity will not affect the performance of the aircraft and require the least trim correction. Thrashing is from the top tank first and then the bottom tank using compressed air. The retardant is reloaded using a pump at 500 gallons per minute. Also, in case of valve failure on dispersing the payload, buckle the design inside of the tank to prevent thrashing. Next slide, please.
Okay, so for the tail design, we considered 4 different configurations: a conventional tail, which is shown over to the right, a T-tail, which is similar to that, but has the horizontal stabilizer positioned at the top of the vertical, a cruciform tail, which is similar to the T, but has the horizontal stabilizer a little bit lower than the top of the vertical, and an H-tail, which is kind of the opposite. It's got 2 vertical tails, each on the extreme end of the horizontal stabilizer. And there's a reason why we ended up choosing the conventional tail. This down selection process began with an analysis of general trends in weight, and this eliminated the H-tail and the T-tail, which each feature stabilizers supporting each other, where the supporting stabilizer has to be reinforced and is therefore heavier. For that reason, we reserved our later analysis for the remaining 2 options. This stability-based analysis, this stall recovery analysis, is about protecting the rudder, or a third of it at least, and the elevator from the turbulent winks coming off of the aircraft when it is stalling. The cruciform tail ended up not working out for us here because the constraints imposed on it by the blanketing conditions of the elevator and the rudder both constrained the vertical position of the horizontal tail with respect to the wing. That caused a problem because the rudder needed to extend 5 feet below the horizontal tail in order to serve as an unblanketed third of the control surface. That raises the tail, the horizontal tail, 5 feet over the root of the vertical tail. Where this becomes an issue is the fact that the 5-degree incline of the dorsal surface of the empennage means that by the time you get out to the 70-foot moment arm of the tail, it's risen an additional 6 feet. So this means in total, the horizontal tail is risen 11 feet into the airstream over the wing. And as you can see by this figure in the center of the screen, that means the horizontal tail is going to be blanketed, even though this is what you need in order to prevent the vertical tail from being blanketed by the weight coming off of the horizontal stabilizer. So the contradictions here couldn't be resolved. So we ended up using the conventional tail. That was our final choice because it's a whole lot easier to fix the blanketing issues in that configuration. You just move the vertical tail forward. What you can see there in that slide on the right is an older version of the configuration. We just move the vertical forward, and that's where we have our design as of now. And that just about wraps it up for the tail design.
So when we're looking at flight controls, we had a main goal in mind, that being stable level flight. We wanted to be as efficient as possible. To accomplish that, what we did was we had smaller control surfaces in terms of the percent of the chord that is a controllable surface, and extended that control surface further along the span of the ailerons of the wings and rudder. And you can see those values listed there on the left.
Fuel system. The only thing this aircraft will be combating the forest fires, which don't have means to pierce the fuel tank of an aircraft in flight. The primary way that fuel will be stored on this aircraft will be integral tanks located in the internal structure of the wings. The capacity is 8,100 gallons per tank. For our aircraft to make the 3,000 nautical mile range requirement with no payload, the total fuel used is approximately 7,600 gallons of fuel. Another thing to consider is the change in the density of the fuel during flight. To accommodate for this, 5% of the tank volume was added as a rule of thumb to prevent the tank from expanding too much during flight. With this new tank volume, each tank in each wing of the aircraft should carry approximately 4,000 gallons of fuel. A total of 8,000 needed gallons of fuel can be stored inside of the wing. This means that there is no need for auxiliary or central fuel tanks located inside of the fuselage. The type of fuel, the engine we choose will accept any type of jet fuel. We chose Jet A1 because the A1 is readily available, and comparing with the others, it has the lowest density place average of 6.57 pounds per gallon. The maximum amount of fuel the aircraft can carry is calculated using this value to be on the safe side and maintain a flight time of 7.5 hours. Next slide, please.
All right, so moving on to the landing gear, I'd like to start by drawing your attention to the figures on the right side of the screen. So at the top, we have our landing gear configuration when we first created it in SolidWorks. And below that, we have an image of the C-130J Hercules landing gear assembly. We really liked the way that they had the housing on the outside of the fuselage, so we took that and incorporated it into our design. So then moving on from that, we chose to go with a tricycle landing gear configuration because of the way that the center of gravity and the weight distribution for our aircraft, it accentuated all the best parts of our aircraft. For our landing gears, we designed them as single oleo strut configurations. For our main rear tires, we used a Type 7 34x11, and you can't really see it in this photo, but actually each strut has 2 wheels per strut for the 4 struts, meaning that we have the 8 tires. During our initial design phases, we actually had 1 wheel per strut, but we decided to add a second wheel for extra safety factors and weight loading. When retracting, it retracts directly into the housing through a vertical motion. And the rear wheels have a pressure of 70 PSI, and they're able to take a load of 19,400 pounds per tire. The contact area of each is 122.87 square inches. And this allows for a very even weight distribution at a very moderate pressure rating. So for our front tires, we used an oleo strut again for a single strut. And for the retracting method, it is going to swing toward the nose and enter into the housing before retracting. Similar to the rear tires, these tires are going to run at a pressure of 68 PSI, meaning that they can take a load of 14,000 pounds per tire with a contact area of 83.09 square inches. With these factors added together, our aircraft is best suited for civilian airport tarmac. Next slide, please. Shamir, your mic's muted.
Okay, now for power plant and propeller design, we decided to go with the Europrop TB400 D6 engines, which we decided using a design matrix, and design matrix being based on which engine would perform the best within our given parameters of the aircraft. Now, at first, the engines were rated for 11,000 shaft horsepower, but we had to scale them up by a factor of 1.35, so that way we can make the dash speed, which means these engines are now, after being scaled up, 14,850 shaft horsepower each. Now we decided to go with a total of 4 engines primarily, so that way our aircraft can perform ETOPS operations or extended operations. The other thing too is the increase in safety. So let's say we're flying for a mission and a mechanical failure happens in one of the engines. Worst case scenario, one of the outer engines. Then we just lost 25% of the power. And you don't need all engines in order to fly. You need all engines to make the dash speed. So at the same time, if one of those engines were to fail, then we can use the rudder to compensate for it. And so that's why we went with a total of 4 engines. Now, in terms of the propeller, at first we decided to go with the 4-bladed propeller configuration. The issue is that it didn't really provide enough thrust to make that dash speed. So instead we decided to switch it out with 8. Now, with this in mind, that means there is a lower efficiency because we have more propellers, but at the same time, our engine, our power plant is able to assist the aircraft in making the dash speed, which is why we went with 8 instead of 4 propellers. The other thing too is that if you pay attention to the right, you can see that we have our engine, but we also have the propeller configuration. For the 8-bladed propeller configuration, we're able to back this up with the data of the Airbus A400 Atlas and Tu-95 Bear, which also uses 8 propellers to power through a lot of their design parameters as well. Now, the Europrop TP400 D6 can actually take Jet A1 fuel. It can take a multitude of different fuels, but we went with Jet A1 because it was the most readily available and also because it was the cheapest. Next slide.
Hi everyone, my name is Dan, and I'm going to be talking about everyone's favorite part of any business endeavor, the money, the nitty gritty. So wildfire severity and frequency is both up on the uptick. So what that means is there's a need for our aircraft, and in addition, there is a gap in the market currently from mid-sized fire bombers to large fire bombers, and ours kind of goes in that little middle range of it. So there's a market for our aircraft, and a cost analysis was performed on our aircraft. It took into account of things like what materials it's made out of, the overall size of our aircraft, the speed capabilities, and then like the running rates for engineers and mechanics to actually construct the aircraft at the time. And this came out to about $6.2 billion to construct. And let's say we had a production run of 50 aircraft, all of them were sold. That would run each aircraft for about $124 million in order to break even. So you'd need to raise more for that for profit. And you may be thinking, oh, that's a lot of money. It is in terms, but to put things into perspective, the Airbus A350 was made by Airbus. You may have heard of them. They're a little company. And that ran them about $3.5 billion in order to develop that over time. And those run about 300 million a pop. So it's not too bad looking at it, 3.5 billion versus 6.2 billion, considering Airbus has had a lot of experience and has made similar aircraft to the A350 prior to actually going on that design route. So not too shabby to say that ours is a little under double the price of that. Next slide, please. Okay, and now for the weight estimation. So it's a pretty crucial role, the relationship for the center of gravity and the center of lift on the aircraft. It's often said that nose heavy plane flies poorly, but a tail heavy plane flies once. And so what we want to do is kind of keep it in a range where it's balanced. So the center of lift on the aircraft, we, without any wind tunnel testing, made the assumption that it falls between the 25 to 30% portion of the main aerodynamic cord, like behind the leading edge of the wing. And so that's kind of a fixed point because it's where the wing is. So we have more flexibility to move the center of gravity around, whether it's moving the payload or moving where certain subsystems are located throughout the plane. So that's kind of the route that we took there. And overall, our plane had a takeoff weight of 193,000 pounds and then an empty weight of 90,000 pounds, with that weight difference being the fire retardant and fuel that's on board. And the figure on the right side of the slide there, that kind of shows what our center of gravity shift looks like throughout the firefighting mission flight, with the borders on the right or left side being that 25 to 30% range of the mean aerodynamic chord. And kind of just from the top, you can see that right as it takes off, it's gonna, the center of gravity is gonna shift forward a little bit actually from the landing gear retracting. And then going to the next point, you lose 25% of the fuel, and then you drop 50% of the payload, and that shifts the center of gravity rear. And then you do the same thing again, go to the next fire, 25% of fuel, half the payload, center of gravity goes aft. And then it's just going to keep linearly going aft as you burn fuel on your way to the next airport or the home airport on the return home, but it stays within the limits the whole time. And it's a very similar thing for the ferry flight. It's just there's no payload added in, so it starts a little bit further back in the beginning, but it ends at the same point. Next slide, please.
Looking at the total design and final, you can see that with the values over on the left of the screen, that our plane does meet the requirements set forth by the AIAA. One of the values I wanted to draw your attention to is the balanced field length requirement of 5,000 to 8,000 feet. We were able to achieve a balanced field length of 1,480. Which we were able to do by creating such high lift devices and such a large wing, which does contribute again to that high weight. But we wanted that availability and usability to improve the options of where our airplane would be able to take off and land should it need to. Next slide.
Okay, and here we have the operating envelope. This is a visualization of the airspeeds and altitudes at which our aircraft can fly, and it is bounded by 4 different curves. The first of those being the breathable air limit. This is imposed here due to the fact that this aircraft is not pressurized and it's not carrying any oxygen. So the crew is going to be breathing ambient air, and they're not to fly any higher than 12,500 feet. Apart from that, there is the line of 0 PS or excess power, which means this is a curve along which the induced drag, the parasite drag, and the thrust cancel out to 0, meaning that the aircraft is going to be just able to maintain straight and level flight at maximum power. Apart from this, there are 2 nearly vertical lines. On the left side, a lower limit of velocity, which is where the maximum coefficient of lift will not be sufficient for the wing to support the weight of the aircraft, and it's going to stall if an attempt is made to maintain level flight. Then there is a Q limit, a dynamic pressure limit, which is represents, I guess, the velocity above which the aircraft is going to possibly encounter structural failures due to an excess of dynamic pressure as it reaches its maximum rated dynamic pressure. And this calculation gives us our first quantitative estimate for the dash speed actually as well. And you can see that on the right side of the PS equals 0 curve, this ranges between 472 and 487 knots. It's quite high, but the review of these calculations is ongoing and it's subject to change. It's quite possible that that is going to go down in the future, but for now, that is what the math is telling us. And that wraps it up for this slide over here.
All right, and that concludes our presentation on the FF1853 today. Once again, I want to say thank you all for coming here to view our presentation, and I think we're going to move on into questions now.
Okay, thank you. So let's first see if our sponsors have any question.
So yeah, this is Rick Miles from Northrop Grumman. Could you go, let's start with your cost slide. So you've got your break-even price as 123.5 million. So that's rolling in all the development costs and stuff like that. That's how much you'd have to sell to just break even, correct?
Correct, sir.
So what would you propose actually going and selling these aircraft for?
Right. So that's for As an engineer, I did my best to try and really dive into that. It's not my pool of expertise. I did see some other aircraft, like companies, they were selling about like 10 million, 12 million above what their break-even price would be to net in profit.
Okay.
And I kind of seen like trends as it goes along that the development cost goes down over time as the plants get more used to making a certain aircraft. So the cost to actually make it will go down. So that will net more profit. And it's kind of varied by company whether or not they choose to maintain that same price or whether they'll follow it down. Kind of like just as the 737 has been made so many times, the price has kind of gone down.
Right.
So if I had to take a shot in the dark, I'd say like 130 to 140 range.
Okay. And then if you go to where y'all talk about your selection of the 27 T4 aluminum. So walk me through why you chose the 2017 T4 versus more, at least what I consider more standard type of aluminums that are used in a lot of the aircraft construction. Why 2017 T4 versus other options?
Okay, so I can answer this one. Because when we calculated the total yield stress, it was around 31,000 PSI. And after looking at a lot of other aluminums, like we did compare a lot of other aluminums, even ones with copper in it and nickel. And it turns out that for the 2017 T4 aluminum, it had around like 33,000 PSI when really what was 32 to 33 PSI when the PSI that we had calculated, the total stress was 31,000 PSI. So that's why we chose that. That's why we chose that type of aluminum.
Okay, it just and again, I'm not as familiar with 2017 as I am with some of the other 2000 series aluminums, right? But I'm used to working with 7000 series aluminum, mainly because with the 2000 series, we tend to have more corrosion concerns than we do with the 7000 series. So that's why I wanted to pull at that a little bit. And then you talked a little bit about there were going to be areas where you're going to use glass reinforced fiber composite. Can you kind of walk me through what areas of the aircraft that was going to be?
Oh, well, that is a little bit, and unfortunately, that's a little bit like unspecified, but it's primarily
the radome, Shamir.
Oh, yes, that's true.
Yeah, we're
Okay,
using
so primarily for the radome design.
Yeah,
Yes,
that's the main element where we added that material. It's just for the permeability so that the equipment can sense things through there. There's not going to be excessive loading in that location. There could be other places to put it, but we have not worked out the geometry and some of the sides of the aircraft to the point where we're going to say we're going to add this elsewhere in the aircraft. Really, this is what we chose for the radome.
Okay, yeah, I guess I would just be concerned whether or not you would actually get the signal consistently through that type of material. Okay, there's different types of composites. Some more expensive composites actually that I'm used to typically working with when you've got to be able to send and receive signals within a radome type design. So that's why I was asking about that. And then if you could go to your landing gear slide. So this is just a comment on presentation. Here, it clearly looks like you got that bottom table out of a Goodyear catalog or something, right? I can't read the numbers on it. I would suggest redoing the table so that it's a little bit more readable instead of doing a cut and paste. Just I think that would get across what you're trying to communicate there a little bit better. And then you were talking about the landing gear. I was trying to picture exactly how the landing gear is moving back up into the aircraft, because I thought you said it just moved up vertically. So it's not pivoting, it's just going straight up. I was having a tough time picturing the action of the landing gear.
Yes, sir. So, oh yeah, Dylan, if you want, you can jump in.
Okay, yeah, I was gonna say I could dive into that. So I guess the best way to describe it is if you think of a jack screw, kind of just like worm gear and working its way back up, because that's how the C-130 does it. And what that allows for is even if they have like hydraulic failure, even electrical failure, in an extreme case, they could still go back there, and it would take a little bit, but they can go back there by hand and turn that gear and still get the landing gear to go down and release. So that just adds an extra factor of safety into it. So that's kind of the reasoning of why we went that way.
Okay. And then
but-
the final question I have, let other people ask questions, is the estimated life of the aircraft.
Good question.
Yes, I mean, there was a time during the material selection where we were going to be able to provide an estimate on the maintenance cycle for this aircraft, and that was going to be based on the fatigue life of the aluminum and the load factor that we were expecting in the wing. But we kind of got squeezed on time for that report, so we have not included that yet. But if you think it's a good idea to get it into the final report, that is something that we kind of understand theoretically and could have later on. I think what we were considering for that was, the span between the maintenance cycles. As for the total life of the aircraft, if that's something that people are known to calculate, we have not taken a look at that yet at all. So maybe we could try.
Yeah, so when I'm used to dealing with aircraft, right, and I've worked on both new and older aircraft, but what I'm thinking is okay, of course you're selling them new, but anytime you sell aircraft, there's eventually an aftermarket where they're reselling the aircraft, and it's all based on how much life do they expect to continue to get out of these aircraft, and especially with the environment you're flying in with the firefighting, right? If you look at failures of aircraft that have done firefighting type things, it typically gets related back to a fatigue type issue that was unexpected because the mission profile that was being flown to fly in to fight these aircraft, they didn't originally, the aircraft they chose for these, it wasn't expected that they were going to be flying firefighting missions. So I think it's a key thing to know how many of those sort of cycles you'd expect in a firefighting type mission to be able to fly on the aircraft before you have to go do some sort of preventative type maintenance at a depot or something to get the plane back up to where it needs to be, and address any areas that potentially might have been weakened by those repeated plunges into a hot area to drop your firefighting foam.
Yeah, all right. I guess we'll add that. Shame on me, I guess. I mean, while I was researching this, I did read about an air tanker that had crashed during a mission, C-130, because it had been operated by the CIA, and they hadn't disclosed what it had been used for. So that we'll fit that into the final report.
No, y'all did a great job here. Just some things to think about moving forward. So good job, guys.
Thank you for your questions.
Thank you, sir.
Thank you for your comments. So I guess Dr. Do you have any question? Okay, he's not here. So I guess just me now. So overall great job. But there are some small things that I want to comment on. They are not necessarily correct, but you probably can put in consideration in your final report. So the first one, well, same as this slide, page 12, the table, and the one I want to comment on is very similar to this one on page 5.
What is that referring to? Page 5.
Page
Okay.
5.
Five.
One more back.
So same thing. That table we cannot see any information. There's no point putting it there. This one, I mean, I can. Let's see if I can do any. So you can see here. Here. What's the point? We cannot see anything. And for the x-axis, y-axis, it's also really hard. So as I emphasized in the class, when you do the presentation, make sure that the audience can get information from the slides if you really want to show the slides. Otherwise, there's really no point to put it here. And my suggestion is that, okay, I agree that you screenshot from some software or anything. If it's really not recognizable, it's not easy to read, you probably can make your own. or you can do something here to make it readable. So that's my suggestion. And I have the same concern on the wing box structure you used 2000, and I have a little concern if it's okay. How can I remove that? If it's strong enough for the spar structure.
Yes. I made a computer in the Excel spreadsheet that we've been sharing for this report to compute the tensile stress at the extreme fiber of those I-beams and a box beam that we had considered earlier on. And when we found that maximum stress, we based our selection of the aluminum off of that. So we eliminated anything that was not strong enough, and we decided to choose something that was a little just strong enough to withstand the maximum stress plus the factor of safety, just that it wasn't too heavy and we weren't over-engineering the wing in this aspect. So yeah, we can double check on that, but it seems at the moment like this alloy will work here. We analyzed that quantitatively.
So I think a more convincing way is that in the structure part, I really prefer that you can show a slide about the structure analysis to show me what is the calculating result. So I can see, okay, the 2017 is good enough, it's not too much, is optimized for our design. You show me some of the calculation result. Because I think for the structure part, the actual analysis is the part that to show your strength as a engineer, as a senior engineer students, right? If I just want to say, okay, you select material, you decide which structure type you want to use, a lot of people can do that. But as senior engineer student, our strength is that we can do actual analysis to prove that, okay, our selection is the best. This material is like optimized for our requirement. Show me some calculation. I'm sure you guys did that calculation, but I think it would be better. I know the 30 minutes cannot include everything, but you need to consider what are the most important information. And I would consider your structure analysis. If you don't have the time to show the structure analysis in detail, that of course, I don't require that. At least show me the result, your calculation result. What is the maximum stress? What is the yield strength of this material? And other candidates prove me that some other candidates, some are not enough, some are too much. And this is optimized. So I'm more convinced on that.
All right, it's understandable. That kind of sucks, I guess, because it's definitely already in our report for that. So we'll end up in the final report, but yeah, we kind of forgot to put it in here.
Yeah, I think you guys really need to consider, like, if we didn't have now, what are the most important information? And the next one is on page 8. So I'm just curious, the fire retardant tanks, you have 2 separate ones and you stack on each other. It's like in this graph, stack on each other vertically, right? My concern is that probably this is not a volume efficient way to put the fire retardant tank if you stack like this, because there are a lot of waste space. Why don't you just use one tank?
We just did the 2 tanks so that it would be easier to kind of partition it into 2 separate drops.
One of the big
Instead-
things too is that this design is kind of modular, that based on what the customer needs for the mission, they can kind of take out the tanks. So say they needed 4 drops at a smaller payload instead of
Okay.
2. It allows for the volume inside of the fuselage to still be there, but then we can modularly pull out the tanks based on what the customer needs at the time.
Another thing that helps there is with sloshing in one large tank, if you only drop half of it, you do have all that fluid moving around. But if you have 2 separate drops, both dropping the entirety of the tank, you don't have the ability to slosh around at all, to mess with the center of gravity there at all.
Okay, great. And the flight controls, page 10. The aileron, you have the airfoil, taper ratio, mean chord, 15 to 90 span of wing. I believe this is a recommendation from the textbook. So what is the actual span? What is the actual aileron design of your design?
Oh, I don't remember the name of it. Julian, do you remember the name of what type of aileron it was? I know it's in the report. I just don't remember it off the top of my head.
I thought you were asking us what exactly was the span of the aileron.
Yes, that's my question. What is that? Is the 50 to 90%? I know this is a recommendation for our general aileron design span of the wing. I want to know what is the specific percentage of your design.
I see. Yeah, that's another figure that was kept in the report, but didn't make it out onto here. I mean, we could try and do the math on it a little bit because we've got a wingspan of 196 feet, and then it goes 50 to 90%, so it's 40% of the wingspan. But yeah, I don't know. Let me get my calculator out just real quick
for the total, like including both wings. So that's what, 35.7 or 33.7 feet for each wing.
Yeah, I think that's 38.8 feet for the ailerons.
Yes. Yeah. Thank you.
Yeah.
And for the landing gear on page 12, I don't know if everything is in the right ratio, but your nose landing gear looks really tiny.
Oh yeah, a lot of these renders are they're distributed throughout the process of designing the aircraft. So in some of them, there are things missing. Like in this one, the empennage isn't on there right, and the nose is just a bullet. The best way for us to portray the final configuration of the aircraft would have just been the renders of the thing with its livery on. I guess. Yeah, we weren't showing the landing gear out in that figure. So I guess you never really saw the relationship between the main gear and the nose gear just by looking at this. It was kind of a very representative of the general configuration with no dimensions. So that is not the actual geometry of the landing gear.
Okay.
It is tenable.
Yeah.
We've calculated it to about 10% of the load on the nose wheel, and the rest of it onto the main gear to avoid the porpoising and all of that. And it balances really well. I tried it in X-Plane after we made it, and I should start doing calculations to make planes in that program more often because it's the best flying thing I've ever modeled in that program. Taking off is easy.
With the renders, it was pretty much we wanted to show the difference in size between the wheels was our primary purpose with this one, and then also showing off our housing on the side. Because that was the primary purpose to talk about, or at least we felt with this slide.
Okay. So sorry.
No, go ahead.
Okay. So here you said the main types you have 8. So let's say 2 main landing gears. Each one has 4 tires.
4 oleo struts. So like I don't have another pencil. This would be one side of the landing gear.
Okay.
Like, let's say the left main landing gears.
Okay.
So we have 2 struts, and then on each of these we'll have
Oh,
one
okay.
wheel on each
Right.
side.
And because we
that.
have a right view shown here, they would all be perfectly in line with each other. So you only see the side of one side.
Oh, okay, okay, okay.
Yeah, I tried to make a mention of it when we were presenting that there
Okay.
were 2 tires per strut.
Okay, okay, now I
Okay,
get
there we go. Yeah, your drawing has it right.
it. Great, now I understand. And thank you for drawing the nice picture. For the next slide for the power plant. So you showed everything here, like what engine you use and how many, and the performance power to weight ratio. So the power to weight ratio is the power to weight ratio of the actual design, right?
No, the power to weight ratio, that was the one, that was from the engine website. That's a lot of this information actually came from the engine website. The power to weight ratio for the actual design was calculated in report 1.
Okay,
And
so let's say
unfortunately-
this is a power to weight ratio of the engine you selected. And I feel like when I want to see a power plant design, I want to see the requirement first. And then you show me what engine you selected, what the performance of your engine, the engine you have, and then I can compare. Okay, if this is enough, it is too much. If this is optimized, right? So I don't see the requirement here. Like for the power plant, what is the power to ratio required? You had that estimation at the beginning of the semester. I think it would be nice if you could put it at the beginning of the power plant. And propeller design, so we can see, okay, this is a requirement, this is our design. Our design is optimized for this requirement. I say, okay, this is best design. Otherwise, you just show me, okay, this is the engine we said, this is a performance of our engine. I mean, how do I know this is best for your design?
Okay, that
Right.
makes it. So yeah, that's on my, sorry, that's on me. What happened was I kind of just put a lot of miscellaneous information. What was really important was really the power that was needed for the engine to propel it to that dash.
Yes, you should have a, so based on your analysis, you should have the power requirement. Okay, you put the requirement at the beginning, and this is the guidance of design, and then you can select everything and have your weight expansion, and then, okay, this is the power our engine can provide, right? And then you can say, okay, it's enough, it's not too much.
Okay.
Yeah, it's better that I can see the comparison of the requirement and know your actual design, so I see that everything is good. And for the page 15, weight estimation. This is central gravity envelope diagram. You have some numbers on the x-axis, but it'd be nice. You can indicate what the x-axis means.
That is completely my fault. I think I blanked during the when I was actually presenting it. So those are the that's the number of feet you are away from the nose going aft on the aircraft.
Okay, so it's in terms of percentage.
No, just in feet.
Okay, in feet. Okay, so it's better that you put it in clear way, so I'm not confused.
Yep.
It's in feet or in percentage, and
Right.
Also put a unit there. And also in your whole report, this is not just for presentation. In your report, make sure that every graph you make clear what is the x-axis, what is the y-axis, what is the unit, everything. So yeah, I think
Right. Thank you. That's my fault. While we have you here, I have a quick question for the final report. Are we following the AIAA thing where it's a 100-page limit, or is it kind of just throw it together? Could it go over that?
I think it'd be nice to keep it like under 100 pages.
Okay.
Yeah. Are you like, do you guys like have too many extra?
We have to see once we actually combine them through, but we've had some like 20-something page reports throughout it. So if we just, it'll take some condensing.
Yeah, because during the semester we have a lot of iteration and analysis, and in the end, it probably a lot of like previous iteration you already proved it wrong. You can just skip it, right?
Okay, perfect. Thank you.
You're welcome. And for the final design, next slide. Okay, so I'm using the one you post on the website. No, you emailed me. No, you submit on Canvas. So I think this one you update a little bit. So you say you put here balance requirement, and our design is 1480. So
Yeah, that's the absolute minimum we can still take off on.
yeah, so I can feel like, okay, that's great. Our balance field length is much lower than requirements. And my next question is that if the customer say, okay, my requirement is 5,000 to 8,000, and you provide a solution of like several times lower, I would say, okay, can you adjust your design to make it that close to my requirement? I don't really care. It's like 1,400 or 5,000. Just redesign it and make it cheaper for me.
From what I understand, that was a byproduct of our design, not so
Okay.
much something we targeted. Because we do have that very large wing, we are able to produce a remarkable amount of lift in such a short distance. It was more of a byproduct that happened to be true, and less that we needed to be this low. How do we get around that?
Yeah. So probably in your presentation, you probably can explain that it's not that we design specific in a way to make our balance field length to be 1480, much lower than requirement. Is because we need to target other things like the range, the speed, and to satisfy those things. And then in the end, we calculate balance length field length is this one. So to make the audience clear that, okay, it is okay that this is, it doesn't mean your design is not optimized. It means that it just like because of other requirements make it this way.
Yeah, that was my mistake. When I was explaining it, I flipped the words by accident, and it was I didn't realize it until it was too late.
Yeah, I feel like why is it like this is much lower? Because if I just see this one, I probably can say, okay, you probably don't need that strong and or that big wing. You probably can make this smaller, make it less powerful, and make the whole aircraft cheaper. So you can just say that in your presentation, make it clear this is generated because we want to satisfy other requirements.
Right.
Yeah. And next slide. First, I think similar thing. You have the blue, red.
Oh yeah, oops. Something got missed. I'm colorblind. I thought that those were two different colors. Those are both blue, eh?
And on the left, everything is blue. I mean, which I know which line represents what it means, but for the audience, how do you expect the audience to know which curve, which line represent what?
Yeah, I was trying to go off of like a model where the audience would depend largely on me. I started labeling the whole figure. So I had that one label on the horizontal line that says breathable air, but then I thought to myself, well, it's going to be the same words next to the figure as there are at the side of it. And for a second, I thought, oh, maybe I can just take all of the wording off from the side and it can just be
you need to change the color
itself. And I talk about that. Could I have done that?
I mean, if you want to make it clear, let's say the left line is a stall limit, and you need to make the stall limit and the line as same color, and the red line you need to use red color for the word. Let's say it's maximum dynamic or maximum speed.
Right.
You need to change the color also of the text also.
Yeah.
So we know which line represents what it is. So
yeah, I just abandoned the thing of labeling it and figured, well, I'll just kind of describe the curves as I give the report. And I suppose that's not the most efficient way to do things, but definitely
make it clear in the slides. And also in the fund report, it's very important that you have that you have something, you need to have something on the side, so people can see what each line represents. And for the store limit line, I think there might be a mistake because I know that store limit is a constant value, but that is based on, we assume that it's at sea level, the density is constant. And now when we plot this store limit,
Yeah, that is
as a function of altitude, it should change. You know what I mean?
Right.
Right now, this should be the true L speed. So true L speed should be a function of the density. So if the density change, the store limit, the store speed should change. So over the y-axis, when the altitude change, it's not constant.
Yeah, I see what you mean. That is a little bit suspicious for the plane to be flying at under 100 knots at, that altitude. I see. Yeah, we can fix that. There's probably some sort of bug in the calculations.
Yeah. So just make sure that you make everything clear, because in the VN diagram, we know that the x-axis is equivalent to L speed. That one doesn't change with density, doesn't change with altitude. But for this operating envelope, the x-axis is the true L speed. So true L speed, it changes with density. So if you change with density, it changes with altitude. It's a function of altitude. Yeah. And also, so the previous slide, 16, page 16. Why the VN diagram you put here? Probably I missed some part. You didn't explain this in your presentation, did you?
I did not. At this point in the presentation, we were getting dangerously close to the time limit.
Oh, okay.
So I kind of skipped over it. I think at this point I looked down and I saw that we had 27 minutes and there was a whole slide left, and I was like, oh no, we're not going to make it. So I just kind of sped through. But yeah, that was just a function of the timing.
Okay, that's smart. I was curious. I mean, like, you didn't explain why you put it here.
Right, I had all these notes. Like I was going to list like our cornering speed and maneuvering speed, and I looked at the time and it's just we didn't have any.
Okay, I understand. So one more question about the VN diagram is that why the right side is not closed? Why you make it open?
Don't have an answer to that question.
It's an envelope, right?
Right.
Envelope should be closed.
Shamefully answer that. From way back when I made this in Excel, I didn't know how to put like a vertical asymptote in Excel. That's literally the only reason. Just close your eyes while that's being drawn, and it looked like that the whole time.
Yeah, now it's closed.
Yeah, see, there you go.
See, because no matter it's operating envelope or this VN diagram, we want to make it closed because we want to show people, okay, within this envelope, everything is safe. On the boundary or beyond the boundary, it's dangerous. If it's open area, what it means, right?
Oh. Right.
Yeah, this figure is perhaps not friendly to the layman. They might end up trying to fly the aircraft at 600 knots. Yeah.
It's like, there's no limitation on the maximum speed. You can fly at whatever speed you want. It won't fail. Is that what I mean? Because it's open.
Yeah,
right. We'll fix that.
The supersonic water bomber. No. Yeah, we'll figure that out.
I'll watch a couple YouTube videos on Excel.
Yeah. So if you cannot make it Excel, just use Photoshop or anything, make it close.
Okay.
Yeah, it's like some detail things to make yourself more professional. And as audience, we don't really care if this is made from Excel or you just hand draw it. I don't care. Right. But I want to see an envelope.
Sure.
Yeah, and some other comments is that I don't see very clear slides on the control stability analysis. Probably it's because of time limitation, but I would prefer that you can cut down some time on other things and put at least one slide on the stability analysis to show that, okay, our aircraft has the stability, right, to prove our tail design is good, our wing design is good, it has non-shear stability, roll stability, and yaw stability. This is a very important property of our design. It's like eventually you have all your design, you have wing design, you have tail design, you have fuselage and everything. You need to prove that your aircraft has a stability. I don't think I see any information on that.
Yeah, we spent a lot of time calculating that, but it did not end up in here. We had kind of a funny process of making the slides where, I mean, there were a lot of, we've got final exams and stuff coming around. So by the time I actually showed up and looked at these slides, I was most of them were already there and I wasn't thinking of adding anything. So it didn't occur to me to I was originally going to look through all of the design reports and add them based off that, but I was just thinking,
Yeah.
they're all here. So I think a lot of us coming in, we just didn't double check to see if there was any content missing and the stability got pushed out. So yeah.
So whenever, no matter is this presentation or the presentation you do in future, like in the industry, or you go to grad school or go to conference, you always check in the end, you check everything in the big picture. Do you have the initial estimation? Do you have the wing design, fuselage design, tail design, landing gear, structure, propulsion system? And in the end, you need to prove that your design is good. How to prove? Stability analysis, performance analysis. This is the proof to show that, okay, our design is good. Otherwise, how can I say that you designed the best design? Right? How do you convince me that your design is good? So at least one page, if it's caused by the time limitation, at least one page to show me that the derivative of the longitudinal stability, lateral stability, to show me that it's within the reasonable range and it has the stability. And also the performance, I see some of the performance, but I don't. I would prefer that again at the very end of the presentation, you can, same as cost estimation, you have a conclusion slide to show me, okay, what is for our design, we did an analysis in the end to and our performance analysis show that, okay, what is the dash speed, what is the range, what is the, I think somewhere you put the the balance filters. I would prefer you put it in a systematic way on one slide. This is our performance analysis results here. It satisfies all the requirement at the beginning. Right.
Okay. So
yeah.
in
So
a sense-
always so always see everything in a big picture, and to see that if everything put in a very logical way, in a very clear way, if because of time limitation, we can remove some details like what material to use, what like that kind of thing, we can skip that. But the important thing is that we have the big structure complete.
Okay. So
Yeah.
in a sense, we're missing the entire mainframe of the presentation. Got it.
So overall, great job. And these are my comments. And I think in terms of the work you have done through the whole semester and also the presentation itself, I think is great job. And thank you for the presentation, and work hard on the final report. Any question for me?
What was our final time?
Yeah, did we go over the time limit at all?
You're fine. Don't worry.
Okay, good. we were worried.
I was running a stopwatch, so I didn't think so.
Yeah, me
You're
too.
fine. Don't worry.
Yeah, me too. By the way, I'm
Uh.
sorry. Go ahead. Sorry, go ahead.
But me? Oh, what question you have?
Well, this isn't a question with the presentation. It's just with my mic. Do you hear me breathing at any point? Because I don't know, the kind of headphones I have, they're incredibly sensitive. The mic is actually a couple inches from my mouth compared to everyone else's mics who are actually on the computer. And so it tends to be and so for some reason my breathing tends to be a nuisance.
It's
So-
okay. It's okay. It's okay. Don't worry about that.
All
I
right.
have been in the presentation since Monday morning. Trust me, your group did really well. The other group, I don't want to comment on other groups. They're not my student. So don't worry about those small things. I think your group did very well.
Thank you.
You're welcome.
All right.
Amir, we don't want you to stop breathing. Keep breathing.
Keep it going.
Just
Make sure keep breathing until at least until the final report. I want to see the report.
Absolutely.
No, do not worry. I actually made a note of all the comments that you made, and we're gonna make sure
Thank
that's
you.
in the final one. Yes. you
Okay,
know,
I've been doing that too.
Oh, yeah.
I'm glad we weren't the only ones. That's why I keep looking down. I've got this notepad just full of paper, full of numbers here.